So we are starting now with some more talks on the OntoTrans system. In particular, now there will be a talk on the translation knowledge base, the OntoKB. This talk will be given by Luca Foschini, who is going to join the stage now. Yeah, he's from the University of Bologna and is in charge of that part of the development in the OntoTrans project. So looking forward to your presentation, Luca.
Thanks a lot, Gerard. It's a great pleasure for me to be here, ladies and gentlemen. And now we're gonna talk a bit more about let's say, what's behind the curtains in terms, especially of the technology. I'm gonna talk about the OntoKB. The OntoKB is at the very core of the OTE, of the Open Translation Environment, and it represents mainly the knowledge base for the ontological data. So let us try to give a first high-level definition of the OntoKB, and especially to motivate why we need it in OntoTrans. So the OntoKB works as the knowledge base, as I told you before, at the very core of the Open Translation environment. It is based on a triple store. And what is a triple store? A triple store is in itself a persistent storage for triples, which means a way to express ontological knowledge in terms of RDF data triples. And as Emanuele was saying in the previous presentation, that's the way that we adopt for expressing semantic knowledge in OntoTrans, following the, let's say, the standards of the semantic web world. Basically, these triple stores, as the basis, they are persistent storages, but then they also do offer more. First of all, the possibility to reason on the triples that they store, and in its turn to produce new knowledge and to make new facts emerge from that knowledge. So basically to infer from the existing knowledge some new knowledge. And in order to do that, typically they also, in these, let's say, in these environments, there are typically available also built-in reasoners that work as engines to produce such new knowledge. In addition to that, most of the modern tools in this area also do offer easy ways to interact with the triple store itself, basically by exposing application programming interfaces to request functionalities and to coordinate and interact with the triple store in itself. So the triple store, summing up, is the basic building component of the OntoKB. There are several possibilities in terms of triple store frameworks, and for those of you who are interested in a detailed overview, we also had a training just in the OntoTrans project, just speculating about the pros and cons of all these tools and products that you see here. Some of them are more open, some others are are more closed in terms of the code, and also, of course, they do offer different functionalities, and also in terms of their inner technicalities, they are based on different technologies. But we don't have time here to go into the details of that. What I want to underline here is just the final choice that for us was Stardog. Stardog is such a triple store, and it's a commercial product which offers, it's very rich and powerful and offers several possibilities. Likewise, it is also well aligned with all the main open standards. And being a commercial solution, it also guarantees somehow that, of course, we do have the support, and it is always kept up to date. And so, in terms of the tool that we use inside the OntoKB for the implementation, we use Stardog. Let me underline, nonetheless, that we tend to implement all the functionalities required by OntoTrans by using APIs that are the standard ones. So not to lock in to the Stardog implementation by itself, but in the future to potentially also move to another different triple stores, and as anticipated before, all of them nowadays expose standard APIs, and so it's fairly simple if you stay on standard libraries to move from one to one another. Going into more detail, what are the main features that let's say motivated this decision towards Stardog in OntoTrans? First of all, it embeds both the reasoner, the needed reasoners, and also it exposes an endpoint for querying the knowledge base through the Sparkql language that I'll go a bit deeper into the next slides for those of you who are not familiar. In addition to that, it offers also very nice graphical user interfaces, which are web-based, so very portable, and that allow in an easy way to administer the whole system. Last but not least, it also offers natively the possibility to ease the deployment of the triple store itself. And basically, it is available in a Dockerized form in Flavor, in the sense that it is possible to very easily deploy the Stardog as a container using the Docker technology, which is, of course, the mainstream nowadays for the container management. In addition to that, it is also well assisted being a commercial product, and so there is a lot of documentation about it and a very nice community that work on this product. As for the APIs are available, the standard ones, and so we are using the Python RDF lib as an API that is standard enough to guarantee not to lock into the Stardog by itself, but also in the future to potentially move to other triple stores that implement the same standard library. So a few words about Sparkql, especially for those of you who are not familiar with it. So as said before, the triple store is storing triples that are RDF triples. So there is typically a need in this area for a language to query such a knowledge base. Most of you are I guess, familiar with the SQL. Sparkql reminds a bit also in the acronym, the SQL language for the database, but in this case, Sparkql is a protocol and RDF query language, and the acronym is like this. So it's kind of recursive acronym, as sometimes we in computer science like to make acronyms, and a specific query consists in a set of triple patterns that are called basic graph patterns. So what the goal of Sparkql, of course, is to extract knowledge. So let me make an example here, just to clarify the concept. As you see here, we have a knowledge base with some triples. And here you can find the knowledge represented as a graph with all the main elements, A, B, and C, and these leaves here that I reported for your convenience and ease of reading here as labels. And we want to extract from such knowledge base through a Sparkql query a subgraph, let's say, and the subgraph where there are available both the elements that are the name and the M box. So as you see here, we will gonna select only A and B, because only A and B have both the elements name and the M box. And indeed, that's in fact the result, the final result of the query, where we want to show, to select, to report the name and the M box. And that's what we are showing here as a result. So, said in other words, this is the way that an expert user can navigate and query the triple store. And the Sparkql endpoint is the entry point where the expert user can, let's say, execute such queries. So getting now back to the open translation environment, an important question is, in OntoTrans, what we do store inside the OntoKB component. This is an important point in our project because the OntoKB is a knowledge base for the semantic data, the semantic information, whilst it is not storing the raw data. Said in other words, we do not want to use the OntoKB as a relational database for raw data, or in any case, let's say a persistent depot for those data that we do consider raw data from experiments and so on and so forth. Why? Because first of all, the amount of raw data could easily explode for some domains, for some experiments, and also we want to let's say enable an environment which is more like kind of a federated environment where the users could maintain their raw data at their premises, if that is the case, without having to move the raw data inside the OT core components. And apart that, of course, there is also a point which is about the performances of these triple store tools, which are typically designed for processing and storing semantic information rather than big data by itself, whilst the raw data might be big data, and that would, if we would store such big data into a triple store would really provoke, in some situations, a tremendous drop in the performance of the tools themselves. For all these reasons, we decided not to store raw data inside the knowledge base, but rather we stored there, of course, the ontological schemas and the individual describing the data somehow. In addition to that, we also do store what we call mappings. The mappings are basically a way to link the ontological concept. In particular, we do have for each application domain a specific application ontology, and the mapping is then a link between that application domain ontology and the actual raw data that are outside the OntoKB. In addition to that, as we will see in the next slides, we do define data models as a way to represent the structure of raw data. The point is that a single mapping could be linked to different data models for different data sources, as we will see. And last but not least, we also store some information about the location of the raw data or how to bind to those, more in general, how to bind to those raw data. So if they are in the database, for instance, the binding for the database and so on and so forth. So this is, from a logical perspective, what we do store in the OntoKB. So as you see here, the whole European material modeling ontology, but then also the verticalization for the different application, which we call application ontology, and then the individuals for the instances of that specific application. For instance, for a specific experiment that we run into that application domain. In addition to that, this is pure ontological information. In addition to that, we have the mappings I was talking you before, which are also available together with the data models. So let me show you an example. So here in green, we do have the application ontology for an application called app3. And also through the predicate maps2, we map these into one data model. And the data model itself, as you see, is a way to link the application domain ontology to the actual data. The actual data in this example is an Excel file, for instance, or a comma-separated value file, if you prefer, with different columns. And so through this mapping as a whole, we can map the application domain ontology concepts into the specific raw data part into the CSV file. Why are data models important? They are very important because given an application domain ontology, we can, through the data model, we can embrace different raw data formats and link to different raw data formats. So for instance, here you have an example with the concept in the application domain ontology, which is then mapped through data model 1 to the column label, whilst the same concept through data model 2 is linked to the name column. And as you see here, we have the same kind of information, but of course with different column names. And so the data models allow for such an integration. And of course, eventually that brings to the possibility to rather easily automate the binding to the raw data by using these mappings that are stored within the OntoKB. From the perspective of the user, how the OntoKB looks like, basically we are leveraging the graphical user interface offered by Stardog, which is a pretty nice web interface that both offers the possibility to show the knowledge as a graph, as you see here, but also, of course, to have the detailed expert text user interface, command line user interface as the one which is shown here. The other part of the core components of the OTE are, apart the OntoKB that I've been talking about so far, we have the so-called OntoRec. OntoRec is for us a smart access point to the OntoKB functionalities. Basically, it will offer specialized for the different application domains a set of APIs that can be easily used also by non-experts that, for instance, do not know Sparkql, by invoking easily such APIs as full-fledged REST APIs, which are the standard for the interaction between services in, let's say, in the nowadays web and cloud-based world. And so, going deeper into details, these are examples of the REST APIs that OntoRec exposes. So, for instance, to return the list of all available databases of triples contained in a specific database, or even to create a new database or send through this REST API a specific query. This is just, of course, for the more expert users that want to express a full-fledged SQL query. In terms of the deployment, we are well aligned with the deployment support that we do use in OntoTrans as a whole in the project. And so everything is managed as containers, as will be also detailed in the next talks. And so basically the OntoRec is itself a container, and the OntoKB as well is in itself a container. And so here, for those who are interested, of course, we leave to you the material. I go fast through these slides that just show the details of how we do compose the two containers that together compose the OntoCore elements of OntoTrans. So the OntoRec and the OntoKB, and their dependencies expressed through Docker files. I will go toward the end of this talk by talking a bit also about how we do interact with the other parts of the OTE environment. So basically, in OntoTrans, as was anticipated also by Gerard, we both do store the knowledge, but the knowledge about the different application domains, but we also have the possibility to manage and transform the raw data, because in some situations it might be the case that these kind of mappings that I was showing to you before, we want to leverage them also to make some transformations on the data. So in order to do that in other parts of the project, we specifically, our colleagues at Sintef specifically focus on how to orchestrate such kind of transformations through a largely well-known pattern, which is called the filter and pipe pattern, to have to define a pipeline and to manage in this pipeline data, transforming them from some initial format to some different format or to some specific output, and in the middle of the pipeline, for instance, by filtering them, and so on and so forth. I'm talking about this because we leverage the same pattern also for facilitating the interaction between these kind of pipelines and the OntoKB. And so in order to do that, what we did was we developed a set of plugins which are specific for the OntoKB that are somehow instances of these filters that you find here. These three instances are potentially working as a data source to interact with the OntoKB and to work internally in this kind of environment as a data source for the semantic knowledge and information extract from the OntoKB. Then another plugin, this one called Sparkql Query, can be used as indeed a filtering component that can filter out only part of the knowledge that has been sourced by the data source component. And so basically, through these plugins, it's possible working at this level to have also kind of a external from the OntoKB external cache where we can work on the data, on these data that are now in memory by storing them, for instance, upon a specific query, and manipulating this data without having to go for all or any query back to the knowledge base. That's very, very useful, and it's very well linked to what will be shown by my colleague in the next presentations. That they will show up what then can be done in terms of even more complex transformation operations on the raw data. What I want to underline here is just that through our plugins, we can, the same way, in the same kind of environments, share the session, we can get the ontological data and we can get the mappings and we can start this process of linking with the raw data, and then they, with their additional plugins, can work the raw data by itself in the same kind of in-memory environment. So here is just a fast list about what it's kind of a preview of a teaser of what you will see tomorrow in the demo. Basically, in the demo, we will show a tour of the Stardock Studio and the graphical user interface for the final users that want to interact directly with the OntoKB. And then we will show some examples of how it's possible interacting with the OntoRec through REST calls, calling the REST APIs. Last but not least, we will also show a live and working example of how we can work with the filter and pipeline strategy pattern that I was showing you before, that internally is called also TAPI as a whole software package. Okay, that's it. So summing up, as I showed you, the OntoKB is our knowledge storage. Indeed, it's something more because it also stores the mappings toward the raw data, which are a strong enabler also for working on the data themselves. And it provides reasoning capabilities, and through the OntoRec, we can facilitate the interactions with the core OntoKB and eventually the Stardock Triple. Important aspect is that we do not contain in OntoKB the raw data, but thanks to the usage of the mappings, we can still bind to and link to the actual raw data wherever they are, because the mappings contain all the information and the data model to map the application domain ontology into the actual raw data. And of course, both OntoRec and OntoKB are well integrated with the remainder of the OntoTrans ecosystem. Okay, that's it. So,
thank you. Thank you very much, Luca, for the presentation, and also, yeah, we're looking forward to the demonstration of that system tomorrow. Jesper is going to talk about connecting things, the OTE API and OntoLib. We already heard a little bit about it, and so looking forward to further elaboration on that from Jesper Fries from Sintef.
Yeah, thank you very much for the introduction, Gerhard. And it was very good with also the introduction Luca gave to it. Unfortunately, Thomas is sick, so I will be presenting this myself. So the idea of the talk is about connecting things using the OTA API that Luca already introduced. These what doing is that we are creating pipelines that connects data sources to receivers. So a data source could, for instance, be an experiment. If doing an EBSD or something, that you have a microstructure can be represented in one way. So yeah, such a pipeline contains first you need access to the data. Then you need to parse it. We have a parsing step that you reading and interpreting the data. Then you mapping it to the ontologies. You come back to that, simply giving it a unique meaning, a semantic meaning. You can, if we are now having a case here where we, let's see if I can get the mouse pointer. So if you have a case here where the data what we pass is in looks like this. It's a the physics is a grain structure, but you have a model here that actually wanted as a pole plot, the same data but represented in different way. Then we need a transformation in here, and the idea is that we built in such transformation here. We have one Luca already introduced a data model. We have one data model represent the past data, but we needed this converted data, the data in a data model that expected by the simulation tool. So we have a transformation that does that, and it is utilizing the mappings to the ontologies for performing its work. And that work can even happen after configuration. It simply happens automatically and very reusable. And finally, we have a final transformation, which could be publishing or running a simulation, which is the case I was thinking about. Okay, going a little more into detail. So a pipeline, first, it follows a design pattern, a software design pattern called pipes and filter. So you have filters that are connected by pipes. So there are many commercial software that are using this pattern here. It's a well-known approach. And the idea is that you can combine, create filters that are reusable and can plug them together into a pipeline. What we do is to standardize on the interfaces to make it possible to make this system pluggable. And it's also important, this part here, that these filters they can be connected, but they are loosely coupled, and there are no very strong dependencies between them. Make it the system much more manageable, maintainable. Of course, in order for such a system to really be pluggable and work, you need a underlying interoperability framework. So, but OTE API itself does not is agnostic to such a framework. It assumes you have such a framework, but you can use different frameworks. In OntoTrans, we are using the Delight framework, but that is not a requirement in order to use OT API. And okay, for these filters here, for instance, a data resource filter, they can connect to many different data sources. And there's also another strategy, it's called a strategy design pattern, so another software design pattern that is used in order to achieve that. If you go one step up, so let's say this here is supposed to illustrate a pipeline. You can actually create modeling workflows by connecting pipelines. So first of all, the pipelines themselves are rather flexible, the filters that you combine, but the pipelines after configured can also be combined into workflows. And so you can see such a pipeline as a reusable, very interoperable component for solving larger problems. Such a work, so the pipeline kind of is about the data flow, describes the data flow, while a workflow, at least in the figure I'm showing here, is more about how the processes of the process flow. And we can see in such a process flow here, we're trying to describe a translation process where the translator is notified and receiving a request, starting a simulation, using the pipelines, resource analyzed and sent back to the customer. Okay, there are several different types of filters that are defined. So we already shown some of. We have the data resource, so that can be either connecting to some downloadable part, can be files or more file specific. Then you are combining a download filter with a parse filter. That first one is able to download it, could be from file from the web, and then the next parsing is using a media type, really interpreting the content. Another type of filter is a source filter. It's also connecting, accessing data, but this is more accessing a service. It could be accessing a database where you are sending a query to that and communicating with it. The result is the same. What you get out is some raw data. Well, it is hopefully in a form of a data model. We'll come to that later, which then can be, for instance, mapped or something. There's a mapping filter that allows to connect to ontologies. It really is a key for semantic interoperability. And as I mentioned, it depends, of course, on an underlying interoperability system. There are filters since, okay, the pipe and filter uses the term filter. So from here on, I will use the term strategy but I'm speaking about these filters simply not to mix with the filter. So we now call it the filter strategy, which is a kind of selecting part of the data set. Then the functions, they are like transformation, but they are lightweight. So they are executed synchronously. It can be a part within a pipeline, while transformations here, they are asynchronous or would always typically end the pipeline. Also common to all filters is that they are configured. So instead of, you kind of change the programming scheme when you're working from a more, you are from a functional where you are defining dedicated function, you are declaring what is what these filters are doing. So you could still call it programming, but becomes more declarative. It's important. This has now been made open source, the OT API. so with OT API, we actually mean now a kind of a family of repositories that are, so it's a framework containing several repositories. So it has a core component that provides, of course, the core, connecting to how accessing to filters or strategies. We have services that provides a REST API. We have the OntoLib, which provides a Python library for the that communicate with the REST services. And then there are some OT API, Asmode and Delight. These provide Atomscale strategies, or strategies that are predefined for working with Atomscale. Some OT API Delight define some strategies that are specific for generic useful for Delight. And then there is also a cookie cutter template. So simply a template that it makes it easy for users to define, create their own plugins and strategies. So the core is simply contains a plugin system for loading strategies, both standard and third party. Then we have it contains some data models for configuring the strategies. It provides a Python library for which the data can be accessed, and in addition, it actually provides some strategies. So it has many functions, you could say. We have the OT API services, which make this provide this REST API. It facilitates creation of pipelines. They are not really manifested in this REST API yet. So here you just see a screen dump from it. What you can maybe realize is that you see here data resource and how it's the access to this REST API. People, if you know the DCAT ontology, you realize that it follows the nomenclature of DCAT, which makes it very easy for users to connect to any kind of DCAT data resources. And then we have the OntoLib, which was the Python interface to OT API, to the OT API, actually to the REST services. And it's actually first in OntoLib that these pipelines are manifested or implemented. And what we see here is just some code, Python code, showing how you are working with OT. So it creates a relatively simple interface for users to work with. You can create a client, then you can define a data resource, and so this would be a strategy, data resource strategy, a mapping strategy, a transformation strategy. Then you simply combine them in a very simple syntax, and at the end you can execute this pipeline, and you actually get the result out of it. So it makes it very easy to work with at a higher level to work with such pipelines. Yes, this OT API plugin template. So that is simply a system for making it easier to create your own plugins. It make it easy for you to make a pip installable package, so a standard package. It contains some unit tests, or at least template code for unit tests to make it easy for you to employ continuous integration and deployment, and also generate good documentation for your plugins. Okay, then we have the Delight part. So Delight is an interoperability framework, and OT API provides a plugin for that. So really what Delight does is that it enables semantic interoperability, making sure that information from a sender can be communicated to a retriever and actually correctly be understood. and it utilizes ontologies for achieving this. Yeah. And the Atomscale modeling is simply using provide some strategies for connecting to using Atomscale model to see here structure for good read. It's utilizing the atomic simulation environment. We have also, of course, in OntoTrans implemented more plugins that are in private repositories. Okay, so a pipeline is actually not transferring data, even though it looks like when you are drawing it up, it's quite efficient. So what it's actually more, you could say, more a receipt for how data is handled, or you could call it a data documentation system. First of all, of course, nothing is transferred before you execute a pipeline. But also that it's not really transferring data before it's executed allows you to set up pipeline and execute it completely behind a firewall. So if you have a company here using the OTA API, they might have their internal databases and some servers, but then they can access the OTA services on the net, use as a broker, and utilizes all services that is provided, and then internally set up a pipeline, and then they can execute it. When they execute it, no data is leaving the firewall. So it allows, I would say, to use OTA API in real use cases, also for companies. So speaking about this filter strategy, so that filter is about data reduction, and you can do that in actually they work in both upstream and downstream. That is a special implementation, right? But it is one example again that data is not really transferred via pipeline. So for instance, if you have a database, of course we don't want to dump the complete database in a pipeline and first at this step here figure out what we're interested in the database. Instead, if you create such a pipeline here with a filter, you formulate your query in this filter here, and that when the pipeline is executed, then this query here is applied and just select the data you are interested in the database. So actually so that is a way to kind of upstream reduce the data for filter. But sometimes, again, you might have large data sets that are not could be implemented in the data resource that is able to pick out parts of it. But let's say it's not implemented, then you have actually a data set that you are completely mapping, and then you have a filter strategy that is reducing just selecting a part of the data set. That could be interesting for a use case where you want this data here in an ontological state, and then you want to connect it to other filters running maybe for this part of the data you want to run a new pipeline, and for another part of the data you want to run another case. So it can be a selection and used in switches. Okay, so let's go back again to Delight. It is an interoperability framework based on data models, and it's an implementation of the soft framework that Thomas Harklin is really the author of and the thinker of. In soft, data models are called entities. And if you look at Webster, what is actually the meaning of the word entities? Means that something that exists by itself. and something that is separate from other things. And that's exactly what an entity is. So it is describe or a data set, something that is self-contained. Entities, they have a unique identity, usually described by a namespace version and name. They contain a human description, some dimensionalities, and some properties. So let's take now a look at a scheme for an entity or a data model. It says exactly what I said. It has identity, description, some dimensions, and some properties. There's also ontology. It's also ontologized, so it's possible here to serialize actually entities as RDF. Okay, if we fill it in now with data, then now we are actually describing the data model itself when we're filling in the scheme. So here we are defining an entity for a person with, okay, the description is a person. It has one dimension labeled n, which means some number of skills, and then we are adding some properties, a name, an age, and a skill, and you can see they have some types and description of that, and one of them has also a shape. What units can they have? Sorry. Oh, what happened now? Ah, I'm sorry. I need to press the wrong button. They can be serialized in JSON format. We can also create instances of the data model, of course. Here you can see a JSON serialization of an instance. Here you can see, here you actually get the numbers. So in this case, we have 4 dimensions, and we associate a name, so a value to the name, age, and the skills. We can see skills has a dimensionality, and so we have reusing this n, which was 4, so we see we have 4 skills here. Yeah. Also, there is a collections. That is a special type of entities, which essentially is implemented as a set of relations. But you can look at it as that contains references to instances and relations between them. So actually a collection is a small knowledge base. So here you see, for instance, a collection here with that is instanted with data. We have each entity you add to a collection has a label. So and it's identify what type of entity is this label, and then the UID to the actual entity, to the data, to the instance. So here there are some instances added with more human readable names, and then you can start to add relations between them. So you have Sherlock Holmes solves crime, and Dr. Watson helps Sherlock Holmes, Moriarty performs crimes, and so on. And this actually allows us to, using these very simple RDF types of relations between entities, allows us to build up very complex data structure. In OTAPI, such collections here are used and shared between all filters in a pipeline. So filters here can add instances and can relate to the different instances and also use relations. So we have this kind of shared knowledge base. It works like that. It's like a small shared knowledge base for a pipeline. Okay. Next step here is that we now want really to go back to this mapping step here and really show that how we can use this mapping to allow to enable really semantic interoperability. So let's say we have a data resource. It we have a data model which is expressing the data that is that you receive. Close to resemble that, so it's easy to create a data resource that creates this data model here. And the same, we have a transformation that needs the same data that we are reading, but expressed in another data model. Now, if you're now using these mappings here, the mapping simply maps, as Luca already explained to us, it maps the properties in the data models to ontological concepts. By doing so, from both sides, we are now able actually to say that this property 1 in the first data model here should be, or maybe we should take the other way around. When I want to instantiate this, I have an instance of this data model here, and I want to instantiate the same data, but as an instance of this data model here. I look at the how this property is mapped to the ontology and see, there's a property in this data model that is mapped to the same. So I can simply take fetching the data from instance of entity 1 and populate the instance of entity 2 with that. This is a very simple example. Yeah, this is actually, okay, I'm coming, this is more or less showing exactly the same, just a little more explicit here using a molecule and a substance. I see time is running out, so I will continue a little faster. It's also possible to do a little more complex mappings or conversions, where you are where you are converting not just properties from instances, but actually full instances. That is also supported by Delight. It's not as reusable and flexible as the property-based, but it can handle more complex cases. And sometimes we cannot avoid it. So it's possible here to build up a catalog of transformations that goes from instance level. But let's go back to the property transformation. So you have a source data model, the instance of a source data model. You want to populate an instance of a destination, and then you can use these maps to relations that we are seeing. It's now possible if you are mapping this one to a concept in one ontology, but it's possible actually to use the same maps for using the is-a relation in an ontology, and maybe map from this ontology to another ontology. That also works. So these mappings, the interpretation of the mappings also actually are able to follow more ontological concepts and even mappings between ontologies. And even more interesting is that we are also able actually to allow transformations to or functions that so a property here that is a function of several properties is allowed also to be expressed ontologically and show very powerful mappings. Yeah, I will skip this slide because of time, but this is an example. We can come back to it tomorrow about how to such mappings here can actually be used to utilize this function and very flexible way to map from one data model to another. And with that, I want to conclude and summarize. So OT API is really a framework for connecting things. It's about data flows connecting sources to retrievers. And with that, I want to thank you.
We can come to the next talk, which will be given by Florina Piroy from TU Wien, and she's going to talk about translator tools. Over to you, Florina.
So I'm going to present you now a little bit less technical content about the work we are doing on defining translator tools in OntoTrans. And this is work done in collaboration with almost all partners in the OntoTrans project. You've seen this picture quite several times, many of you. I would like to draw the attention to these blocks on the outside arrow, which Michael Neuske presented earlier in his introduction to how to address innovation challenges. These are the main phases in the work of a translator when he or she handles an innovation phase. Now, in the previous presentations, you have seen the internals of what OTE, the OntoTrans environment, can do. You have seen how the innovation challenges were approached ontologically, how we processed the data, transformed it into a way that it makes sense to us. And you have also seen how the OntoTrans knowledge base is structured and some ways of interacting with it through the OT API functionality. So, but as a translator, you want a certain level of transparency with respect with these technological solutions presented to you. So what you will see in the following slides is exactly this. It is our attempt to address some of the challenges the translators face, to assist them in solving innovation challenges and if possible with easy access and friendly reach into prior knowledge or possibly similar and previously solved challenges. So in other words, what we aim for with the tools is to, we develop in OntoTrans, we want to make the translation process more efficient and more accountable, and we want to have support for clear guidelines, either development or integration, and also provide evidence for best practices. And we want to use semantic methods and ontology representations for solving these manufacturing challenges. Now, the tools, the translators that we are working on are these three. So we are working on a common graphical framework to work on the innovation challenges. And this is linked to a system that allows a user to search for information for previously executed innovation challenges, and also a tool, a set of tools for data analytics. So basically, these tools allow you to interact with the data you have previously collected or generated in, and this interaction is done in a meaningful way, semantically. Now, the last two tools, the exploratory search system and the data analytics, they can be used also independently of the common graphical framework. I will give you now more information about each of these tools in the following slides. Good, so one of the first tools we want to present is that is intended to be the point of entry to the OTE, to the OntoTrans environment for a user. That is, we want to have a graphical user interface, and this interface, what we are working on is specific to each industrial application case, and it should be a user-friendly way of interfacing with features that are, again, use case dependent. Some innovation challenges need to interface with simulation platforms. They need to, other may need to do reasoning on data, or you would need to query and browse data. You would need to do some data analysis prior to running simulations. So now let's look at the graphical framework we are working on. So as I said, this is specific to each industrial application case, and each application has a customized workflow-based interface wizard that will provide non-expert users and an easy starting point for providing the user cases with a control interface according to their specific requirements. Then now these are after we have done in the last more than a year ago already almost a couple of discussions with stakeholders and industrial partners in the OntoTrans project. We collected from them their needs and how this interface should look like, what are the best ways of interacting with it. These are just a very short list of these requirements, but there are way more which we provided in a deliverable to the EU Commission. Now, these requirements are in the process of being concretized in this interface you are seeing. So what you see here is a design prototype. It bears almost no functionality, but this is where we are going to. So a user, as a translator or a user looking at an innovation challenge, this would be your entry point to OntoTrans, to the OTE. And for this specific cases we are working with and creating the demonstrator for, we have these 4 applications. We call them application or innovation challenge. On the left-hand side, you have some further information about what else the OTE may be, maybe some other links to documentation and so on. And you also have links to other tools which can be accessed from this interface. Now, once you select an interface, once you select one of these 4 cases, let's say you will see tomorrow a demonstration using this composite prepreg process optimization example. And for this innovation challenge, there are 2 types of processes. We can look at 2 types of workflows. Either we look at target porosity of the surface, or we want to optimize the curing process. Now, notice that on the left side, the workflow has been displayed for the specific innovation challenge, and the user will see we have a very quick overview where exactly in this process he or she is. Again, you will see a demo on this tomorrow and how it will work. Now, behind the scene, the way this wizard, so what we call in computer science an interface wizard, is this sequence of screens which guide you through the whole process you are doing. So what happens behind the scenes is that the wizard actually interacts. So this is the wizard level, and here you have the OntoTrans environment level, and here you might have some other external environments which you might need to access. And this is now just an example of the many possible processes, but many possible interactions between the wizard, the common graphical framework, and the OTE. And these interactions, like this arrow, for example, they trigger calls to the REST API, which were mentioned before. They might trigger calls to external simulation platforms and so on. That might trigger requests for validating the data and so on. Good. So let's look at the next tool for translators, and this is now the exploratory search system, which my team at the TU Wien works on. And first of all, I would like to explain to you what exploratory search is, just to be on the same page, all of us. And now, traditionally, when you search for something, traditional search is query response oriented. You type some questions, you have a very clear information need. I want to know which is the longest river in South America. You type this question there, and you get a list of answers. So this type of search is very good for well-defined information needs and goals. Now, exploratory search is different because it enables a user to do information-seeking tasks by learning and investigating, and it should offer, and it does offer, a higher level of interaction with the data. So let's say that I would like to learn more about Stanley Kubrick, and an exploratory search system would show me a couple of things here, and I see here, oh, he actually wrote also some books, and I would start clicking here, and I would maybe come later back, and I would look into his work in the doing the Shining movie, and then I would go and explore the information space about the horror movies in the 80s. So an exploratory search system is something which supports you in exploring a given information space. Now, in the last decade, there are quite a number of exploratory search systems that have been published, and many of them are applied to knowledge graphs. Now, knowledge graphs, the definition of what a knowledge graph actually is still contested because it was from the very beginning not well defined. But in this context, let us think about of a knowledge graph as being just an RDF data set on which we impose an ontology. And then we can reason on this data and deduce facts. So here on the left, you have an RDF graph where a person called Bob is interested or enjoys watching this painting, and this painting has been created by Leonardo da Vinci. And then on the right-hand side, you are adding now semantical information to this data here, where you say that Bob is a person, Leonardo da Vinci was a person, then there is an image, and this person likes to watch this image often, and so on and so forth. So you are adding semantic knowledge to a set of data. So now here, what I'm showing you is this entry point to the exploratory search system that we are designing for the OntoTrans environment. So it's you will see tomorrow more closely how this works. Basically, this for this one specific innovation case, the users can explore the knowledge base. And look for what type of pre-preggings are there, what kind of phrasings do I have in there. Now, if I have a search box here, which will allow me to, will display me this information in a way which will help me understand how things are related in between them. Here in the back, you see how the data itself must be represented such that an exploratory search system can make use of it. And then this data here, this data here, we are let's say extracting it from the OntoTrans environment and also possibly combine it with external data sources that are processed through the OTE-lib, because you've heard before that raw data can be very, very large, and we don't aim to store it in a central location. Now, on this slide, you see two further nice features of this exploratory search system we are developing. Basically, here on the left side, you have the possibility to issue Sparkql queries, which Luca just showed us about an hour ago, I think. And you also have the possibility to explore the hierarchy of classes that the knowledge base, the exploratory system has access to, is using. And tomorrow during the demo session, you will see again how this can be used in a complete workflow. Now, these functionalities all still under development. So if you get to try the system, don't get angry with us if things don't work as you expect. Good. So I'm coming to an end soon. The third set of tools for the translator are data analytics, and these are now very much in discussion right now, because each use case needs a different set of data analytics tools and applications. But the goal is to have qualitative and quantitative data methods to have more insights and observe trends in your innovation challenges. And these data analytic tools will also aim to give more context to the exploratory search system I've just shown you. And we also want to integrate data science methods in OntoTrans use cases. How this can look like. Data analytics tools could, for example, provide what-if simulations when the intention is to avoid real-life experiments that might not succeed. I would like to know beforehand what the cost for that running those experiments would be. So and maybe possible outcomes with some confidence interval, confidence values. Or you could do specific data quality analysis on data that is incoming to your process to check if that data is appropriate for your innovation challenge at all. You could also, so basically all these tools can show you how everything is interconnected in your set of data, or also across innovation experiments in your innovation challenge. So that would be a really nice ultimate goal we'd like to reach. You want to look from all the inputs in your data, which are the dominant ones, what are the exceptions to the rules, and so on. So the possibilities are quite wide. That would be it. So I have arrived to the end of my presentation, and I'm happy to not have used the time from your lunch. I invite you to join the demo session tomorrow, and thank you for your attention.